Good morning, students. Welcome back to Signals and System online video lecture series. In this class, I am going to discuss about the introduction about the third unit, that is continuous time signal analysis. So we know that the continuous time signal is a one in which we can have the signal at every instant of time. The best example for the continuous time signal is a sinusoidal signal. In the sinusoidal signal, we can have the signal at every instant of time. That continuous time signals, how we are going to analyze them, we are going to study in the third unit. Fourth unit will be discrete time signal analysis. So, in the continuous time signal analysis, that is in the third unit, we have to study the continuous time signal analysis. We know that a signal said to be a continuous time signal if it is available at all instant of time. A real time naturally available signal in the form of time domain. That means if you take any signal that is real time naturally depends on time, and a real time naturally available signal is called as time domain signal. That means we represented the signal with respect to the time. X of t, if you go with the x of t, that is a continuous time signal in which x of t is total, x of t is the amplitude of the signal, whereas t is nothing but it is the independent variable, that is time. Independent variable, that is time. So whenever we are representing a signal, with respect to the time, then that is called as time domain signal. However, the analysis of a signal more convenient in the frequency domain. The point is very clear. So far, whatever we have discussed, the signals, all are time domain signal only. All are time domain signal. That means we have studied the signal with respect to the time, such as x of t we have discussed in the form of x of t, y of t. Like this, we have studied some various types of signals. All these signals, nothing but these are the continuous time signals, and these are the time domain signal. That means what? If a signal represented with respect to the time, then that signal is called as time domain signal. But the analysis of a signal is more convenient. In this entire third unit, we are going to study the analysis of the continuous time signal only. But analysis of that continuous time signals are more convenient when it is in the frequency domain. So far we have studied the continuous time signals only, but if the signal is there in the frequency domain, then analysis of that signal will be very, very easy, and it is more convenient. So there are three types of transformations methods are available for the continuous time signals. There are three types of transformation methods are available to analyze the continuous time signals. One is a Fourier series, another one is Fourier Transform, and the next one is a Laplace transform. So here I am going to talk about the Fourier series and the Fourier Transform. In the second unit, we have discussed the Fourier series. Fourier series is nothing but it is an infinite sum of trigonometric functions, and which are used to model the periodic signals. This Fourier series is applicable. Fourier series can be used to model the periodic signals only. These are used to model periodic signals. Periodic signals, nothing but these are the signals after particular specific time duration the same signal is going to repeat itself, then that signals are named as periodic signal. The best example for the periodic signal is the cosine and sine signal. Cosine and the sine wave. So this Fourier series can be applicable for periodic signals only. So here we have the three transformations. One is a Fourier series, another one is a Laplace transform, next one is a Fourier transform. All these three transformation techniques are used to analyze the continuous time signals. Continuous time signals can be analyzed by making use of the three transformation. One is Fourier series, another one is Fourier transform, another one is a Laplace transform. In this class, I am going to give the difference between the Fourier transform and the Fourier series. In the second unit, we have discussed the Fourier series. Fourier series is nothing but it is an infinite sum of trigonometric functions which are used to model the periodic signals. And we know that Fourier series is applicable only to the periodic signal, that is signals which repeat periodically over the interval minus infinity to plus infinity. That is, not all periodic signals can be represented by the Fourier series. The point is very clear. Anyway, this Fourier series is applicable only to the periodic signals, but not all the periodic signals can be represented by the Fourier series. Fourier series having some limitations, that it can't model all the periodic signals. It will model, or the Fourier series can be used to represent some specific periodic signals only. Some of the periodic signals cannot be represented by the Fourier series. That is the limitation. It cannot be applied to the, and as well as it cannot be applied for the non-periodic signal that are aperiodic signal. The point is very clear. Fourier series can be applicable for the periodic signal, but all the periodic signals are not represented by the Fourier series. One limitation. So anyway, non-periodic signals and aperiodic signals cannot be represented by the Fourier series. This is the disadvantage. So the Fourier series cannot be applied for the aperiodic signal. This is the major drawback of the Fourier series. However, all the naturally produced signals which need processing will be in the form of non-periodic or aperiodic only. The natural signals, most of the natural signals which can be represented, which will be basically aperiodic signals only, and that aperiodic signals can't be represented by the Fourier series. Fourier series is limited to the periodic signals only, and one more important thing, and all the periodic signals are not represented by the Fourier series. So that the most of the signals available in the world, such as aperiodic signals only, then that aperiodic signals cannot be represented by the Fourier series. So that we are looking for the another representation that is called the Fourier transform. That is Fourier transform. So now we have discussed just now. I told that so far we have studied the signals such as x of t, y of t, that are nothing but continuous time signals. But when the signal is continuous time signal, such as called as time domain signal, but when the signal is in frequency domain, that is very convenient to analyze. So far we have studied the continuous time signal such as time domain signal. That means we have studied the signal properties with respect to the time. If that signal properties are represented, with the frequency, that is more convenient to analyze the signal. If the signal, that means what? If the signal is, however, the analysis of the signal far more convenient when it is in frequency domain. So that I am going to talk about the two things now. One is time domain, another one is frequency domain. Time domain and the frequency domain. Here the point is very clear. Analysis of the signal is more convenient. Analysis of the signal is more convenient when the signal is represented in the frequency domain. When the signal is represented in the frequency domain, then the analysis of that particular signal will be more convenient than time domain signal. So far we have studied each and every signal with respect to the time domain. That means what? We have studied the signal properties with respect to the time. So that I am going to explain what exactly the time domain, what exactly the frequency domain. Time domain, it is the way of analysis of a signal with respect to the time. Very simple. We are going to analyze the signal with respect to the time. In the time domain, the signal or a function value is known for all the real numbers. Signal or the function value is known for all the real numbers for the case of continuous time or at the various separate instant of time in case of different time, in case of discrete time. That means what? Here, in case of time domain signal, if you go with the continuous time signal, that is a continuous time signal. For every real value of time, we have the one particular value of the signal. For example, if you go with the square signal, this is a continuous time signal. Assume that here for every finite value, for every real value of the time, we have the signal. This type of signal representation is called as time domain signal. In time domain signal, for every real value of time, there will be a value of the signal. And if you take any continuous time signal and for every finite value of every real value of that time, we can have the signal in case of continuous time, in case of discrete time and some specific time instance, and the time instance also real values only. That means what? At specific real values of time, we can have the signal, and that particular representation is called as a time domain. So best example for an oscillator is a tool commonly used to visualizing a real world signal in the time domain. If you go with the oscillator, that is a CRO, we can see all these two signals, and that is generating the signals in the time domain. It is generating the signals in the time domain. And coming to the frequency domain is nothing but where the time domain is very simple. It is a way of analysis. It is a way of analysis of a signal with respect to the time, and here it is a way of analysis of a signal with respect to the frequency. The way of analyzing the signal with respect to the frequency, that is called the frequency domain. It is explained as that how much signal lies each given frequency band. In the frequency domain, what we are going to have exactly? For example, that means what? Here we have represented. Here this is x of t. And this is y-axis, this x of t is the y-axis, and this x of t is nothing but this x-axis is nothing but time. In case of frequency domain signal, x of t is going to be the x of omega, where omega is the frequency, and this y-axis is y-axis is about x of omega is that is magnitude of the frequency amplitude. Here now this x-axis will be omega. That means what? It is a way of analyzing. It is a way of analyzing the signal. It is a way of analyzing the signal with respect to the frequency. Here we have analyzed and we have studied the behavior of a signal with respect to the time. Here we are going to analyze the signal with respect to the frequency, so that this type of signals are named as frequency domain. In the frequency domain, exactly, for example, here this y-axis is x-axis is nothing but frequency, and I am defining one frequency band, that is 10 kilohertz to 20 kilohertz. 10 kilohertz to 20 kilohertz. And the frequency domain, we are come to know that within this band, what is the strength of the signal we are going to study. That means what? By making use of the frequency domain, we are going to we will come to know what exactly the strength of the signal in the given specified band of the frequency. Now this is called, it is a band of frequencies. X-axis is what? X-axis is the frequency. If you take any two frequency on the x-axis, that is going to define the band of frequency. In the frequency domain, we are going to study how much signal strength we have in that particular frequency band. That means it explains us that how much signal lies within the each given frequency band. A frequency domain analysis can also include the information on the time shift that must be applied to each sinusoid in order to be able to recombine the frequency components to recover the original time signals. So in this chapter we are going to discuss about the Fourier transform, which is mostly used to analyze the periodic signals, and can be used to analyze the periodic signals also. It overcomes the limitations of the Fourier series. Now we are going with necessity of the Fourier transform. Here the Fourier series is having the disadvantage. It is confined to the periodic signals only, but all the periodic signals are not represented, not analyzed by the Fourier series, so that it is the disadvantage. So that the Fourier transform is employed, and it can be applicable for the periodic signals, and as well as some of the signals can't be represented by the Fourier series, so that periodic signals also represented or analyzed by the Fourier transform. And the Fourier transform, one more thing, Fourier transform is nothing but it is a mathematical tool which converts the time domain signal into the frequency domain signal. The 2 points I wanted to conclude now. Fourier series is having the disadvantage or limitation, that is Fourier series can be applicable for the specific periodic signals only, some set of periodic signals only. That means it is not going to applied for the all the periodic signal, so that whatever the signals cannot be represented by the Fourier series, that can be represented by analyzed by making use of the Fourier transform. That means what? Some specific periodic signals, and all the periodic signals can be analyzed and represented in case by making use of the Fourier transform. And Fourier transform is also a mathematical tool which converts the time domain signal into the frequency domain. Time domain signal is nothing but it is a way of analyzing a signal with respect to the time, and whereas frequency domain is nothing but it is a way of analyzing the signal with respect to the frequency. With respect to the frequency, in the when the signal is there in the frequency domain, it is more convenient to analyze the signal. That means what? When the signal is represented in the frequency domain, we will come to know the strength of the signal. We will come to know the strength of the signal in the given frequency band, in a specific frequency band. And so that the 2 points from the Fourier series, one is it can be applicable for the periodic and aperiodic signal, and the second point, it is a mathematical tool which converts the time domain signal into the frequency domain signal. So that first we should know the periodic signals, and after that we have to study the aperiodic signals, how the Fourier series can be applicable for the periodic signals and the aperiodic signal. I am going to continue this lecture. So that here in this Fourier transform we are going to apply. In the Fourier transform we are going to study the Fourier. We are going to study the periodic signals and the aperiodic signal representation using the Fourier transform. Then how the time domain signal will be converted into the frequency domain by making use of the Fourier series. I am going to explain in the further classes. So that I am going with the periodic signal definition. A signal which has a finite pattern, and which repeats itself at a regular intervals of time is called the periodic signal. Very, very simple. Periodic signal is nothing but it should have a finite pattern. That means what? It should have a finite pattern, finite shape, and which repeats itself at the regular intervals of time. That is called the periodic signal. And a signal which does not repeat at regular intervals of time, then that signal is called as a periodic signal or the non-periodic signals. And mathematically we can prove that here. For example, here periodic signal is nothing but what? For example, here I am going with the one particular signal. This is a signal, assume that. So now this is a periodic signal I can call. This is the signal which has been repeated. This is the signal is there from 0 to t, and the same signal has been repeating, and next from 2t to 3t, 4t to 5t. Likewise, the signal it is having a finite. It is having one definite pattern, and this definite pattern has been repeating itself. Itself at a regular interval time of that is t, and from minus infinity to plus infinity, then that signal is called as periodic signal. Mathematically we can write that periodic signal is like this. That is about x of t. We have what? We have this is x of t. Here to here we can call x of t. X of t is nothing but x of t plus capital T also. That means what? Here to here whatever we have the signal, the same signal even there at t plus capital T. Capital T means what? This part. After this part also we are getting the same signal, so that we can call these type of signals are named as periodic signals, and from minus infinity to plus infinity. If the signal doesn't satisfy this condition, then that is called as. So now we can call it is x of t, and it is t, and here we are having the signal is like this. So it is called a periodic signal. The signal, if this is a signal from 0 to t, and this signal is not at all repeating after the specific time interval, and so that this particular signal is named as a periodic signals. So here mathematically a continuous time signal like x of t is called the periodic signal if the condition x of t plus t is equals to x of t only, then that case is called as periodic signals. Normally all the power signals are the periodic signals only. Best example for the periodic signal, that is if you go with the power signal, that are periodic signals only. And if you go for the aperiodic signal, the best example for the aperiodic signal, energy signals are the aperiodic signals. We have discussed the power signal and the energy signals in the first unit itself only. So that normally power signals are periodic signals. Such signals can be used. Such signals Fourier series can be used for the analysis. Energy signals are non-periodic signals. Such signals Fourier transform can be used for the analysis. Fourier transform can be used for periodic as well as non-periodic signal. This is about the what we can say, it is a periodic and aperiodic signal. This is about the introduction of the continuous time signals. Then what is the necessity of Fourier transform? What are the drawbacks of Fourier series we have discussed. Now I am going to conclude this session with the one more topic, that is a periodic signal by the Fourier integral, that is nothing but Fourier transform. Just now we have discussed that Fourier transform can be applied for the periodic signals particularly, and sometimes Fourier transform can be applied for the periodic signals also. The periodic signals which can't be represented, which can't be analyzed by the Fourier series, that can be analyzed by making use of the Fourier transform, so that non-periodic or periodic signals can be represented with the help of Fourier transform. We know that Fourier transform provides effective reversible link between the frequency domain into the time domain. That means what? It is a mathematical tool which is used to convert the time domain into the frequency domain, and I am going to give some of the examples now. See this one. For example, I am having the x of t. It is a time domain signal on which I am applying the Fourier transform. Fourier transform, it is a mathematical tool, so that it is a time domain signal and which will convert into the frequency domain, and this is the Fourier transform representation. We have the time domain signal, that is x of t, on which we applied the Fourier transform, and this we can get the frequency domain, that is x of omega. Here x of t may be it may be periodic signal or aperiodic signal, because we know that the Fourier transform can be, this may be periodic signals and aperiodic signals, and this we know that the Fourier transform can be applicable. Fourier transform can be applicable for the periodic and as well as aperiodic. By applying the Fourier transform on a continuous time signal, that can be convert the time domain signal into the frequency domain, that is x of omega. The Fourier transform of x of t is defined as, for example, we have the x of t. Assume that we have x of t. It is a x of t, and we wanted to convert that is into the x of omega, that is a frequency domain. So that what we have to apply? We have to apply the Fourier transform. In short, we can call it is ft. Fourier transform we have to apply, so that the resultant signal will be, we can get a x of omega. So that I am going with the standard equation now. X of omega, in what we can get? X of omega is a frequency domain signal. We can achieve this frequency domain signal from the time domain signal, that is x of t, by applying the Fourier transform on the x of t. Fourier transform on x of t is given as x of omega is a frequency domain signal that can be achieved by applying the Fourier transform on x of t, that is integral minus infinity to plus infinity x of t into e to the power of minus j omega t dt. That means what? We have earlier what? Earlier we have x of t on which we applied the Fourier transform. This is, then we got the frequency domain signal, that is x of omega. X of omega is nothing but it is a angular frequency. If you wanted to represent the same, in the normal frequency, that is x of s, x of f is equals to, we can have integral minus infinity to plus infinity x of t into e to the power of minus j. Omega is nothing but what? We know that it is 2 pi f into t dt. Here the point is very clear. X of t is a time domain signal on which we applied the Fourier transform, so that we are getting the frequency domain signal. That is the equation is what? X of omega is a frequency domain signal we can get by applying the Fourier transform on the continuous time signal, such as x of t. It is a time domain signal. Here x of t is a time domain representation of the signal, and x of omega or x of f are the frequency domain representation. Similarly, x of t can be obtained from the x of omega. This is called as Fourier transform. Fourier transform. In the case of Fourier transform, this is a Fourier transform. For example, I am having x of omega. X of omega is nothing but what? It is a frequency domain signal. I wanted to get to the x of t, that is a time domain signal, and in that case we have to apply the inverse Fourier transform. That means what? we have the frequency domain signal, but we wanted the time domain signal. We wanted the time domain signal, so that we have to apply the Fourier transform, inverse Fourier transform. We can call it is the inverse Fourier transform. If we apply the inverse Fourier transform on x of omega, that is a frequency domain signal, we will get the time domain signal. That means what, here we can have x of t, it is a time domain signal. In what way we can get? By applying the inverse Fourier transform on x of omega, that is 1 by 2 pi integral minus infinity to plus infinity x of omega. We are applying the inverse Fourier transform on x of omega, so that we can get x of t e to the power of j omega t dt, d omega. And if you wanted to go with the another form of this equation also with respect to the regular general frequency, that is x of t is equals to we can write integral minus infinity to plus infinity x of f, this is x of f into e to the power of j 2 pi f df with respect to f. So like this we can have the Fourier transform and the inverse Fourier transform. Fourier transform can convert the time domain signal into the frequency domain, and the inverse Fourier transform can convert the frequency domain into the time domain for its analysis. So that in the next class I am going to solve some of the problems based on the Fourier series, Fourier transform, so that how the Fourier transform can be used to convert the time domain into the frequency domain, so that you are going to understand very clearly with those problems. Thank you, students.